Okay, welcome. So thank you for coming. This would be a talk where I'm going to introduce you to some functional programming constructs and a bit of a motivation coming from Python. So hopefully, if you are familiar with Python, I will make a smooth transition into some functional programming constructs. Then I'm going to introduce you to Spark. Given those functional programming constructs, we will have an overview of how programming with these constructs can help us make scalable programs with Spark that can work in a cluster and be used to transform large data sets and deals with data that is bigger than what would fit in a single machine. And then when we have gone over the initial bits of Spark, I'm going to extend a bit in some concepts of functional programming in Scala. So that can help you in case you want to use Scala with Spark or standalone, and most of the concepts are universal and apply to any functional programming language. So be it Scala or Haskell or Erlang. So I think in any way they are useful concepts to learn because they can make you a better programmer, even in an imperative language like C++ or Python or Java or Kotlin. And more languages are getting functional programming concepts incorporated. So if you have been following latest Java developments, you can see that with each standard they introduce some of these concepts in the language, like the ones that we will see, options and lambdas and things like that. So let's get started with the motivation for functional programming. I would argue that functional programming helps you produce better code. It can relieve some of the burden of flow control. It can help you control side effects. And it can also help you with improved error handling, and we will see why later. It can help you as well produce more reliable programs. And it can ease the burden of testing because you can use the type system to ensure correctness. Instead of writing a lot of tests, you might take advantage of types to verify that your program is correct. And this is often the case with strongly typed functional programming languages where the type system is very powerful. You can do more with the types and less at runtime. Let's put an example. So this is a function that I was working recently. The goal of this function, this is Python code. So as you see, I'm using typing to annotate types. And the goal of this function is to calculate the PDF or the histogram of a sequence of elements. So basically, we get a sequence in, and we want to return a sequence of tuples with the element that we got and a frequency count, normalized frequency count. Okay, so is there any suggestions how we should go about implementing this? You can unmute yourself and I'll propose an approach if you want. Any takers? Okay, I guess not. But I think the first inclination of many of us would be to, I cannot see the messages, sorry, I have only a single screen. So I'm not aware if there is something in the room, you can unmute yourself. I think the first inclination of any of us would be maybe to write a loop, right? So we can get the default dictionary. This is a construct from Python that is going to, whenever you access a key, is going to have a default value. So we can just loop over the elements, increase the frequency, increase the total count, and then just iterate once through the dictionary and divide by the total. and this returns the list of, so if we give a list of elements, this gives back what we want. So a list of pairs with a normalized frequency. So let's introduce two functional primitives that will help us write this in functional style. So I guess you're familiar with this. So map and reduce. Map is just a function that will take a sequence and apply a function to all the elements of the sequence and give you back a sequence with the elements transformed. Very, very straightforward. Many languages have it. And reduce is similar. Reduce is going to take pairs of elements and repeatedly apply the function until you have just one final value. So it's going to reduce the list pairwise. So let's try to implement our histogram with MapReduce. So I'm going to use this functional library from Python. It's called PyFunctional. And yeah, you can check it out. I use it regularly in my code. So we get an initial list. So in this case, I use some random set of elements. You can see them here. And when you call this seek function, so that's kind of the main constructor for this library, is going to create this object where I can apply map and the other functions, map, reduce. In this case, I'm going to just, it's similar example to the basic Spark example where you count words. In this case, we just map to pairs of the element and one, so then we can reduce by key and sum the frequencies to get sum the counts, right? So the result of this is pairs of elements and counts. And then we need to divide by the total. So for that, we can use something similar. We can do again, just get the values of the counts and then call sum. And the result is the same. We get the count sequence and again transform it to divide by the total and calculate the normalized frequency. We sort and convert back to a Python list, and we get what we expect. And you might ask, okay, what did I gain, right? I just basically wrote the same code, but with map and reduce. But what this will allow us to have some benefits, and I will try to bring it up to you. Let's see how the function finally looks like. So there is less state, right? Because we don't have these intermediate variables. We are not mutating elements like a count. This is parallelizable, right? Because when we have the map function, we can potentially execute the map function in parallel. The same as reduce by key. So if we see them side to side, you can see that we are not mutating the frequency dictionary. We are not accumulating results. We are not also changing the total variable. So arguably, state and mutability cause a lot of bugs in programs, right? For me, the code is also easier to read. It's less nested. It's kind of linear. So when you read a loop, the first thing you read is I'm looping through something, but I don't know what it's doing. But when you read like in this style, in functional styles, you read map, okay, I'm doing something for all the elements. So it's actually, you have one variable less, right? You don't even have the variable for the sequence. You're just passing a function. Yeah, so let's say there is also referential transparency. This means that the functions that we are using, so the function that we pass to reduce, for example, is a pure function, right? So pure function has no side effects. We can replace this function by its value. It doesn't have any internal variables that we are changing. So this helps in terms of what I was saying before, bugs, parallelization, and it potentially opens the door for scalability. And that's why we can now then set the tone for Spark. So building on these constructs, we can then see how we can use these primitives to.
Pedro,
Yep.
what do you mean by referential transparency slash pure functions?
So referential transparency means that since the function is pure, we could replace it by its value. So if you have a function like this that doesn't have x, y, imagine if this function would depend on the time or in some state variable or some global variable, then it's not referentially transparent because you cannot replace it wherever you use it, right? You cannot replace the function by the result of the computation.
Thanks, Pedro.
Does it make sense?
Yes.
Okay, so let me switch to the Spark part. So I guess you guys are familiar with Spark. You have probably, if you haven't used it, you have read about it. Spark is a cluster computing software. It's written in Scala and extends MapReduce model to queries, SQL queries, data frames, and stream processing. And it's very powerful because it abstracts over cluster infrastructure and related complexity. It has also, it's faster than the previous generations of systems like Hadoop because it uses in-memory intermediate storage. And you can use it to process structured data like tables or semi-structured data like JSON and XML. Spark has several components, has language support for Scala, Java, Python, R, and has a set of additional libraries, Spark SQL, that you can use SQL statements to process data frames. You have MLlib, which is a distributed machine learning library. It has a graph library, GraphX, and has support for streaming. And some of the base libraries of Spark is Spark Core, which is basically the core of Spark. Then you have the RDD API on top. We will go into detail what RDDs are. And then you have the data frame API. Data frame, probably you're familiar from Python. I think the Pandas data frames were inspired in Spark data frames. And you have a cluster management software because Spark usually it can run standalone in a single instance, but usually when you want to deploy it in production, you will run it on a cluster. And then you have the problem, okay, how am I managing this cluster nodes? So you have different options there. You can use Yarn, which is another Apache software that you can use with Spark. You can use Mesos, which is another cluster management software. And you can also use Kubernetes. I think this is experimental in the latest versions of Spark. And you can read data from different storage data sources. You can use local files. You can use HDFS. This is Hadoop file system. It's a distributed file system. You can use S3, relational databases, or NoSQL databases. Basically, any data source that you can access with Java, you will be able to ingest the data into Spark. So what's the architecture of a Spark cluster? So when we execute our Spark application, our Spark application is basically a Scala program. that runs on the driver node. This is called the driver program. And you have a Spark context object that is basically where you access most of the Spark functionality and machinery. So through this Spark context, you are going to, this is going to communicate with the cluster manager and the worker nodes. The worker nodes have different executors. These executors, they are basically GVMs that are going to run tasks. And yeah, so you have several tasks per executor. And there is many tunables for that. And when you have Spark running in production, tuning is an important part of it. And the most important variables are the number of cores that you are going to use, is the max number of tasks per executor, and the maximum amount of memory per executor. So you have to usually fit that to the types of instances that you are using and the topology of your cluster, let's say. And I'm going to explain a bit what are the key Spark abstractions and concepts. So when you have a job, which is basically a parallel computation consisting of multiple tasks. The RDDs, this is a bit of a weird name, but basic is the basis of Spark. There is a paper, if you search Google RDD paper. So when they created the Spark, they discuss what is an RDD, what kind of design decisions they choose. Basically, the RDD is a collection. Think about this as a sequence. It's a collection of elements. An important part is that this is immutable. It's partitioned, so RDD it's distributed across your cluster. It enables efficient data reuse, fault tolerant and parallel. So what it means basically, when you have a set of files or a sequence, you are going to convert it in an RDD. So you are going to convert any kind of input data to this immutable partition data structure that lives across your cluster storage. And then you can manipulate it through transformation. So you can do map, filter, reduce, join, group by key, on all these kind of functional constructs that we introduced before. You have tasks which are operations happening on RDD partitions. So when you do, like before, remember we had a sequence and we do map or filter. So we are going to create a DAG of operations that are going to be executed on our cluster. So we will have the DAG that transforms the execution plan of the RDD lineage into a physical execution plan. And on top of that, we have data frames, which is an abstraction that provides two-dimensional data structure of heterogeneous types. The important thing also about the RDDs is that if you lose a node, you lose a working node, it's fine, because the cluster is going to recreate intermediate states. So you can have worker nodes failing and joining the cluster, and since you know how to generate all the lineage of RDDs up to a point, it's basically going to recreate the data that was needed. And you can persist at some intervals in the middle of the computation to have kind of a snapshot. So you can control that a little bit by controlling persistence. But this is basically what's giving you fault tolerance. So you're not going to lose data if worker nodes go down that's expected. And that's thanks to RDD abstraction. So let's see how we create an RDD. It's not, it looks simpler than it was sounding in the beginning. So it's very powerful, but basically when you use it, it's simpler. That's the magic of Spark. It's presenting this complex concept of data distributed across the cluster in a way that it looks like a sequence, right? So in this case, I'm calling range, which is basically like range in Python. It's giving me back a immutable range. Think of it as a list. So from 0 to 100. And I'm calling SC parallelized. I'm using this SC. SC is the Spark context, the object that I told you before that is basically doing all the Spark magic. So we are saying we have a sequence and we put it into the Spark context and we get back this RDD object. So you see this data is of type RDD of int. So it's an RDD of integers. It's a parallel collection RDD, which is the base class of this RDD. Basically, we have created an RDD now. And we can do any transformation. Let's say we want to just double the element, so we can just calm up, pass a lambda in Scala. The lambda syntax is you can use with a fat arrow, similar to JavaScript if you're familiar. It's a bit less noisy than Python lambda, but it does the same. It's just a lambda function. The important thing to notice here is that here nothing happened, right? So if you see doubled is an RDD of int. We don't have anything, we haven't computed anything. We just have created another RDD, a lineage of RDDs, basically. We just have a transformation. So we could say that this is a lazy computation because no computation has happened yet. Yeah, I'm just showing you that the class of this double is map partitions RDD, because we apply the map operation. So it has internal different kinds of base classes where depending on the transformation you do, the type is different, but basically it's an RDD. And if you want to run the computation, we can just here filter only the even elements, and we call collect. So collect, there is a set of functions that both in RDDs and data frames, they are going to trigger the computation. So in this case, as you see, even is an array of int. Array is one of the base Scala data structures. So actually here the computation happen and we get the results. But this is only because we call collect. At this point is the operation schedule and run. And we can see that the RDD has a member function, which is called partitions. And usually this is important when it comes to distributing your data in your cluster. So in this case, it created 32 partitions. So if my cluster is 64 machines, obviously I'm going to use only half for this. This is a very trivial computation, but this is an important factor also to consider for your computations, and you have to consider your cluster size. So if your cluster is big, you might want to have more partitions so you efficiently distribute your computation. And as always, when you're dealing with Spark and Scala, the Scala docs are the main source of documentation. So if you Google RDD Scala doc, you can find RDD documentation. Usually we use data frames in Spark because they are a bit more powerful, but the same applies. So the Scala doc for RDDs and data frames is very useful. Lists all the functions and it's very complete. It's generated automatically, like in Python when you run strings. My main source of documentation for Scala and Spark would be the Scala docs. So let's see the second the abstraction on top of RDDs in Spark, which is the data frame. Most of you are probably familiar with Pandas data frames, and so data frame is basically a strongly typed collection of objects that can be transformed in parallel using the functional or relational operations that we saw before. Very similar to Pandas. So basically we can, in this case, we have a sequence. A sequence is a generic Scala type that is like a list. So, and we convert it to data frame. So this is a feature of Scala that you can have functions applied to, so you can import a module and this module could add functions to existing data structures and classes. This is also something that you can do in Swift. So again, another feature that is coming to to current programming languages. But basically, you could is basically converting the sequence to the data frame. And we can then show it, and we see that we have a data frame of, I put a column label, name, age, and weight. So let's see how can we do computations on this data frame. So let's try to have some weight gain, right? So we have the data frame and we can index the column with a string. So in this case, df weight is going to return a column object. And we add 15. So what we get back is a column. So again, we didn't do any computation. This is just a column object that it represents adding 15 to a column. So it's not doing anything yet. So if we want to run the computation, we can say, okay, I'm going to apply this computation to my data frame. So I'm going to do df select accepts a column. So usually select is similar to the apply function here. But since weight gain defines the column plus 15, when I do collect, I'm going to get the weight column with the additional gain weight. So if you remember, let's go back. The weights were 65, 60, and 80, and now we have 90, 75, and 95. So we had some weight gain, unfortunately or fortunately, depending on your goals. And we can do similar with other functions. So for example, filter, if we want to get people with age bigger than 20, we can do this. Again, you see that this returns a data set. So this is not actually doing a computation. So data set of row is a data frame. It's a type alias, is the same. And nothing has happened, right? So the same story that before. If we want to really trigger a computation, we can do, in this case, we do show. We can do, there is other functions. For example, we could convert back to a sequence or collect or sum or count. Any of those functions that are going to trigger the computation.
Pedro,
yeah.
just clarification. In the previous one, is weight gain a function, or is it in line 50? Is it implicitly thought of as a new column for the data frame?
This is a column and a column object. So basically, since you are adding 15 to the column, it's creating another column object recording that computation. So it's nothing has happened. It's just another object. It's the same as when you do rdd.filter or .map. You get another RDD, but you have just described the computation. You haven't run anything. So think of it as creating the list of operation like a tag. That then when you do collect or you do something, then this whole thing is going to be passed through a query optimizer, is going to generate an execution plan, and then it's going to run in a cluster. So it abstracts all this crazy stuff that needs to happen to execute this on a cluster.
So now what I meant was, in terms of the syntax, it's a bit surprising. Like, for instance, in line 50, we are not saying val something like df.weight gain equal to blah blah blah, right? We are just saying weight gain, and that has the type column. But is it like, is it now as if a new column has been added to df, or
no? It's just you can have created a new column object that is kind of standalone. It's just a variable. It's floating there. So only when you apply it to you use it on the data frame. So we do df.select. Only then you are saying, okay, give me a column when I add 15, and then collect. So give me the results. So I put this example basically because of that, because it's a bit surprising, or it helps you understand these kind of things that if you will go into the console as your first contact with Spark, is a bit confusing. It's like, okay, I want to sum into a column and I get another column, but where is my data, right? So yeah, this column doesn't have any data. It's basically just a class that describes that you are adding 15 to the column.
Yeah, thanks.
Okay, so yeah, if you have any more questions, just feel free to interrupt me. I think, yeah. So let's see a bit. I think that example is clear. Let's see a bit the difference, summarize the difference with Pandas. So in Scala Spark, most of the functions on a data frame accept this column expression that we saw before, and it's going to give us back another data frame, data set of rows. But in Pandas, Pandas is a little bit different, right? So Pandas is eager execution. So if we reproduce the same example in Pandas, if we want to filter by age bigger than 20, you see that the data frame is going to return a series, a Boolean series. So Pandas is mostly passing Boolean series around. And when you index the data frame, here line 30, you're basically passing a Boolean series that is selecting the rows that you want. And it is similar, but it's very different because as you saw in Spark, you are describing your computation and you are not actually running any code. But here in Pandas, you already calculated this series, right? So by the moment you are indexing the data frame, you already have a Boolean series that is going to give you the rows that you want. So Pandas, we could say that is eagerly executed versus Spark, which is lazy. Yeah, any questions about Spark and data frames? That kind of concludes the introduction to Spark. So if there is no questions, I will go to the last part.
Pedro, I have a question on a Spark. So you mentioned that if worker nodes, like it's in the middle of the computation, and if the worker node dies, you control the snapshot frequency, right? When to take a snapshot or when not to take, right? So how do you guarantee the data durability in that case?
So we saw that the RDDs are immutable, and you have a graph of how you created the RDD first from this sequence that you had. So Spark always knows for your computation, always knows how it created, originated from maybe some files, some log files, or some stuff from S3. And it knows all the operations that needs to apply to this data to get your final computation. So if in this process you lose a worker node, it's going to figure out how to reproduce this RDD, this part of an RDD that was lost because your node stopped working or malfunctioned. So it's going to redo the computation needed. In case you have some snapshotting in the middle, so if you have a chain of operations and some of them are expensive, let's think about you're running some function that takes a little bit of time to compute. If you persist, there is a .persist method on RDDs, then it's going to use some of these snapshots that you have on the local disk of the nodes. In that case, it's going to do it from the snapshots that you have intermediate. But think of it as since you have the lineage of the data, then you can reproduce the data at any point in time because you have this. It's connected to the referential transparency and pure functions that we were talking about before, right? You can go back to the data at any point. Does it make sense?
Yeah. So one another question that makes me ask that who controls this? Like, like realize that master node dies. So do we have like notion of central nodes or something, a master node here?
Yeah, we have the driver program and the cluster manager. I don't remember the details where who does the failure control. I think probably it's a shared work between the cluster manager and the driver program. So obviously the driver program is aware of the status of the cluster. I don't know exactly the details how this works, but I would say that this has to be on the cluster. It's a responsibility of the cluster manager because it could bring up additional nodes for you. Also, since now it also supports Kubernetes, it can then replace the faulty nodes for you, right?
Yeah. Okay. Thanks.
You're welcome. Okay. So with
hey,
that,
Joe, another question. Yeah. So for Sandero, do we support RDD or do we support the data frame or both?
you can use any. So those are classes available in Spark, and those are abstractions that are available for you. Usually, I think currently people tend to use data frames because they are more powerful and they're kind of easier to reason about, and the API is quite complete. So unless you really need to do something with RDDs for some reason, you're fine staying at the data frame level. So RDDs is like a lower level abstraction that you might want to use, I don't know, in case you have a simpler computation or you want to have a bit more fine-grained control or do something. But mostly nowadays people are using data frames, or even more abstracted, people are using SQL queries, because you can view your data frame as a SQL table kind of thing, and then you can apply SQL. You can use SQL to do data frame aggregations and things like that. So you don't even need to do the Scala expressions. You can just evaluate a string, a SQL string.
I see. Thanks.
Okay, so let's go to the final part. I don't know how much time I will have, so I think we have less than 20 minutes. So let's see where we get. Basically, the final part is given that we have introduced a bit of functional programming and Spark. Just to go a little bit further into functional programming and introduce you to some concepts that can help you understand what kind of features Scala and other functional programming languages offer to you. It's obviously it's not a lot of time to go through some of the concepts, but it can help you see, okay, what is there, what do I need to learn, what more can I study to learn. At least you have an overview. So the first functional programming language was Lisp in the late 50s. And most of these concepts apply to any functional programming language. So once you learn these concepts, actually you can read Erlang code and you can translate them to Haskell. If you want to learn Haskell, it's much easier to learn once you have learned Scala. Given that Scala has a friendlier syntax, it's a C-based syntax. You can use a lot of Java from Scala, and you don't always need to do functional constructs. So the good thing about Scala is that it's very flexible language, right? So you can use it as a better Java. You can then dip your toes into these functional programming constructs. But if you get, if it's too complex, or sometimes you just want to program your code with a loop, and that's fine, right? That's what I like about this language, that doesn't force me to do functional programming style. I can also do imperative if I want. And for some things, imperative is fine, right? If you are reading from a buffer, things like that, usually it's easier and it's more clear if you do imperative style. So it doesn't force you to. It gives you the flexibility to do however you want. And some other languages don't allow that, right? For example, Haskell is much more strict, and you have to adapt to the FP paradigm. So I will try to cover a few basic constructs from functional programming, algebraic data types, and pattern matching. Optional, which is my favorite feature and the first thing that you come across when you use a Scala or a functional programming language. Higher order and polymorphic functions. This is a mouthful, but basically it's just, you have done it in Python many times, maybe without realizing. It's just basically passing functions to functions and doing interesting things. Then I will tell you about the immutable data structures, which in Scala you have both mutable and immutable data structures. And we saw that in Spark, the constructs are based on immutable data structures. And a bit more about pattern matching. So pattern matching is one of my favorite features of these kind of languages, and I miss it a lot when I'm programming in Python. So let's define a class, case class. In this case, a case class in Scala is basically a read-only class. You can think of it as like a name tuple in Python. So we just define a person that has name, last name, age, weight, height. And we create an instance of this class. So in this class, I create a Pedro, right? It has 39 years old, 67 kilograms, and 164 centimeters. and let's say we want to calculate the BMI of a person. So if we can use pattern matching for that, and pattern matching allows us to match the inner fields of this class. So in this case, we know that we have a person object, so we don't need the 3 first variables. So we have the underscore, meaning that we ignore them. Some people also use that kind of idiom in Python. And we capture the weight and the height. And then we just apply a function. Basically, we divide the weight by the height and meters and square, and they should give us the BMI. Yeah, so this is basically pattern matching. It's nothing more than this, but it's very powerful. You can do much more, but this is the basic idea. So case classes are a specific example of what we call product types. We can call it conjunction. So they are immutable, as we said before. And to make changes, you have to create a copy. So if we want to create a case class and we want to change the name, I mean, obviously we could create a new one, right? But whenever you want to change something, you create a new one. So in this case, trivial example, we create Mary, so we have to call .copy, change 2 of the members and get a new one. I think in Python, if I remember correctly, name tuple works similar. So we call these product types because the set of possible values, it's the Cartesian products of those types. So the class of the set of possible values of person is for all names, all the last names, and all the possible values that types can get. Another example of product types are obviously tuples. We have also some types, which we can also call disjunctions. We can think as instead of an AND type, we can think as an OR. So if we define a hierarchy of errors here, we have a base class error, and we define validation error, which extends error, and runtime error, which extends error as well. When we have an instance, we know that it can either be a validation error or a runtime error, but not both. That's what we call it sum types. So it will be a disjunction. Let's put an example. So how these sum types can help us write better programs. This is very powerful, and I think there is not enough time for me to convey how powerful this can be for your programs. But think about an example where I have some HTML string that I parse, and then I get some tag, right? And tag will have the name of the tag and some attributes, some generic attributes. And when I parse a string, obviously I can have 2 cases, right? I can have a case where I get what I wanted, which is a tag, or I get some error. So we can express that on the type system. So in Python, for example, we might get a none, or we might get what we wanted, and we don't really see that from the function definition. And in case of a Scala, the compiler will check that, okay, you really need to pass a tag or an error. Either it's another class that basically has this conjunction of types, right? So either it's just a Scala construct that tells you, okay, it's either a tag or an error, and can be the one on the left and the one on the right. And the compiler is going to check that. And that's very powerful because, I mean, for error handling, you can obviously use what you can use. You can use error codes. You can do like Go, for example, right? You always have to return maybe something or a tuple of something and an error code. Or in C, you're always returning integer as error codes and giving back outputs on your parameters. But with these kind of constructs, you can say, okay, I'm returning something, or I'm returning several things, and the type system is going to check, are you really returning what you wanted? And this obviously helps a lot with writing correct programs. So in this case, if we combine what we saw before, the pattern matching concept, if we do something on a string and we call parse, so we can use pattern matching on the result of parse to decide what we do with what we got. So if we have something on the left, which is a tag, we can do something. Or if we have something on the right, which is an error, we can do something else. So the triple question marks is basically syntactic sugar in Scala that is going to throw unimplemented error. It's just a placeholder because just leaving the code out. I'm not implementing anything, but still this compiles, but it will not run. And the most important class that I would say when you dip your feet into functional programming is optional. And this is something that is coming to many programming languages nowadays. So I think Java has optional now and other languages. Unfortunately, in Python, none is, usually we use none, but it's not really an optional because none does nothing, right? Basically, it doesn't have any functions that you can use. So I will try to convey why this is powerful. So let's have a motivation from Python. Let's say we have some HTML. This is a real example that I had while doing some code parsing HTML. You want to get a tag that might or might not exist. Or let's say we are expecting a paragraph, a link, and an image. So when you use something like an XML parser or Beautiful Soup, something like that, you can find yourself in this situation. So we can assume that we have, this is a Python type annotation. So we have a get function that is that you pass a tag and is giving you an optional tag, let's say, right? So we will have to build something like this. Okay, I'm getting the P, I'm going to get, if P, then I'm going the A, I'm going to try to get the link, then I'm going to try to take the image, and then if everything succeeded, do something. But I mean, obviously, this kind of code is going to end up like very nested and it's not very good code, we could say, right? So we would like to do something different. The big problem here is that we could get a none when we do get, and we need to handle this case repeatedly. So enter monad. The monad is basically a very scary name that they use in functional programming, but I'm going to just tell you that it's actually very simple. So a monad is basically just encapsulating something in another class. So if you have some class A, some type T that could be an integer, you have this M, the monad class that can be, for example, in this case, an optional. If we say optional of an integer, is just you wrap this thing in another class. And this optional obviously can be the integer itself or can be nothing, and that's it. So as before, it has two possible types, let's say, right? So you can have an int or you can have a nothing. So let's see what the Scala option monad is. I can show you how it's defined, and this is from the Scala documentation. So you have this ceil abstract class. Ceil means that it cannot be extended out of the file where it was defined. So you have an option of some type, ignore the plus for now. And you have a final case class that inherits from option, extends option. So basically, an option can have some, can have an instance of this type. Some means that it has something. That's why you pass here value to the constructor. So if you say some parentheses 5, it's like you're creating an option that has an integer. Or you can have the case where it has none. So none extends option and doesn't have any value. And the most important operations that we can call on this optional is map or flat map. And let's not get confused now by flat map, but let's see what is map. Map is basically as before. We apply a function that takes an A, in this case, the type that we define the option, and returns another different type. So we could return a string, do some computation, return another type. And obviously, you get an option of the second type. So this allows you to chain operations on these options. And you can get option after option. And only in the end, you care, okay, was there something inside? If there is something, you expect the final result. But you can also apply these operations to nothing. And it's still fine, right? So that's actually very useful. That you would think, okay, why do I want to apply these operations to nothing? But it doesn't change your program if there is something or there is nothing. So you don't need to, like in the motivational case in Python before, you don't need to handle the cases because the class handles the cases for you. So let's see how this works. So for example, we can create a maybe string. In this case, we put a string value. We can calculate the size. So we do map, and then we apply, this is a syntactic sugar to say just a lambda that calculates the size. So the underscore is telling you, okay, a parameter. And we can just print the size and use a bit of pattern matching. So if the option is something, then you print, okay, the string length is whatever. And if it's nothing, we print the string is empty, and that's what you get. So we have combined map and pattern matching to do some computation. And then, as I was saying before, you can change these operations, and we see here the case when you have a value, you can do map, change some operations, and you get what you expected. And also, you can also in the flat map case, it's basically the same, but the function that you pass returns another option. So it's kind of symmetric itself. The function is returning an option, but it works the same way. It's just that the type of flat map, if you remember before, it takes an A and returns an option. So it's just a way that to apply the function, but this function is returning an instance of the monad itself. It's very useful, even though if it's not self-evident here. So, and the case where I have none. So, for example, here I create an empty option of int. If I apply those functions, I get none. So as in the motivational case before, if I would like to get the tags, I will just chain those operations, and then I will get either a result or I get none. And then I don't need to do all this if-else handling. And obviously, the program is easier to read and more robust. Yeah, so the options allows us to chain operations and types that might be known for safety and without if-else blocks. So this is basically how the rewritten program from the motivational program from Python would be written with optionals in Scala. Now let's go to higher order on polymorphic functions. This is another mouthful, but basically I think you have done, if you are familiar with Python, you have done it many, many times. So one basic construct is a partial function. So this is also in functools in Python. So basically what we have a function of AB, and this returns a C, and we want to go to another function that just takes a B. So basically we want to fix the first argument and return another function that only takes one argument. So there is only one way to solve this. You can see a bit how the syntax in Scala works. You have here, this function is generic. So this is like a template in C++. So you have 3 generic types that are the types of the arguments. And these are compile time. These are done at compile time, basically, right? And you pass a function of 2 types that returns 1. And you want to get what we said before, just a function of 1b to a C. And there is only one way to do this. And basically, in Scala, you can omit the return. And here is basically we are returning a function that takes a b and is using f by fixing the a parameter and using the b from this function itself. Basically, it's like returning a lambda. So this basically looks more complex than it is, because if you haven't seen the Scala syntax before, but I hope that now it helps you understand a bit better the Scala syntax for functions. So the type definition for a function and yeah. And let's have a concrete example. For example, if we do partial, we get this function that concatenates a string, and we pass d, we get another lambda. And then we can invoke this function that was returned, and we get the result. We get the light. Similarly, we have currying. Currying is going to take a function of several arguments, and we can apply chain functions one argument after another. So similarly before, there's just one way to do this. I'm going to speed up a bit because similar example. So we can use partial from the before example. And in this case, if you see the result, you basically got a function and you can chain the function calls to get the final result. I think we are almost out of time. I'm almost done. I was going to show you, let me show you the last slide about data structures in Scala. So you have, as we said, immutable and mutable data structures, and you have similar data structures as the other programming languages. So you have sets, hash sets, you have sequences, indexed sequences which are vectors, strings, and you have linear sequences like list, string, queue, stack. So this is all in Scala doc. Yeah, I will skip over the list example because I think you already, this is very trivial, and I don't have time to go through this, so let me jump to the final conclusion. So there is much more in functional programming that we have gone through. You have other things like higher kind of generics, futures that allow you to describe computations that will happen in the future, implicits, more things about monads, higher rank polymorphism and dependent types, but these are not in Scala. And yeah, just a bit of conclusion. So FE constructs helps us build reliable programs that use the type system to verify correctness at compile time. Things like Spark can leverage functional programming to scale computation. And you can create more scalable and parallelizable programs with better control of side effects and better resource utilization. And yeah, for large programs, it can be easier to maintain and reason about. And that's it. Thank you for attending. I think we are almost in time. And yeah, thanks a lot. Do you have any questions?
Yeah, Pedro. Which IDE you recommend for the Scala?
I recommend IntelliJ IDEA with the Scala plugin. So yeah, that's the one I use.
Okay.
Yeah,
okay.
IDEA with Scala plugin, and
okay.
yeah, it works very well.
And Java 8 also support the functional programming on the string. What's that compared with the Scala and Java 8?